This video is about algorithm analysis. What do we mean by algorithm analysis? Well, we mean to develop an understanding of the characteristics of the algorithm used for different input parameters. Why would we want to do that? Algorithm analysis helps us predict the performance of algorithms. It helps us compare different algorithms, and it helps us choose good algorithms. So frequently there is more than one type of solution to every problem. Take sorting. Remember that long list of sorting algorithms from the sorting video? There was insertion sort, bubble sort, merge sort, selection sort, quick sort. Each one of those uses a different algorithmic method. So if you do algorithm analysis, you'll develop a good understanding of how the algorithm works. And this also leads to improvement in your algorithms. They become shorter, simpler, and more elegant. When we do algorithm analysis, we actually are thinking about computational complexity. So, what is computational complexity? It's just a way to analyze an algorithm. It takes into account how difficult or how efficient or how fast the algorithm is. And you usually evaluate it in terms of the amount of time that the algorithm takes, which we call time complexity, and the amount of memory that the algorithm takes, which we call space complexity. So let's look at time complexity. In terms of algorithms, the time an algorithm takes is basically equal to the number of operations that are in the algorithm. And when we do time complexity, we want it to be independent of the programming language and the computer used. We can do this by remembering that algorithms are a sequence of steps or operations or commands. And the more steps or operations there are in an algorithm, the longer the algorithm takes to run. So our measure of time is actually a measure of the number of operations. So what is an operation? Well, an operation is anything that uses an arithmetic operation like addition, subtraction, multiplication, division. When you compare two items, that's an operation. When you swap two items, that's an operation. When you copy or save something to the disk, that's to your hard drive, that's an operation. Accessing a list or reading something in memory is an operation. And how many times you go through a loop will affect the number of operations. So when you're looking at a sorting algorithm, you're looking at comparing operations. So each comparison is one operation, and swapping or copying operations, where each swap or copy is an operation. And when you're looking at searching algorithms, when you're comparing two items, that's an operation. How do you figure out what the time complexity is? Well, there are two ways to do it. One is that you can do a calculation. You can look at the basic loop for each of the algorithms, or the basic recursive function. You can count the number of operations that occur in each loop or recursive function, and put a time value to that, and then figure out how many times the loop is run. Or you can run the program for different types or amounts of inputs. You end up looking at a best, worst, or average case. The best case is the case of the time complexity of solving the problem with the best input size. The worst case uses the worst input size, and the average case is just the average amount of time it takes to run any problem. Let's take a look at the time complexity for the two search algorithms we saw in the search algorithm video. We were looking at linear search and binary search time complexity. We're not going to really focus on the best case because that's really trivial. On the best case for a search, you find the item you're looking for the very first time you look. And we know that's really unlikely. We're also not going to focus too much on the average case because, one, it's awfully difficult to calculate. I mean, it's not always the worst case divided by 2. It can be very nonlinear. And so we're going to focus on the worst case. So you can calculate the worst case search for both the linear search and the binary search, and you can derive an equation that's dependent on the list size, n in this case. So for a linear search, we know that the worst case situation is the list size itself. In a binary search, because you keep dividing the list by 2, it ends up that the worst case search for a binary search is log base 2 of the list size n, and then you would add 1 to that value. So if we had a list size of 1,000, then the worst case search for the linear search would be 1,000 searches, and the worst case search for a binary search would just be 10 searches. That's how you would look at time complexity for algorithms. Now, when we look at memory or space complexity, one algorithm may require more memory than another. If memory is scarce, then space complexity or the memory used is important. But this is not such a big problem anymore because computers have lots of memory now. But data sets are also getting bigger and bigger, so sometimes we still have to consider it. And when we do, then there's often this time-space trade-off. I mean, what you really want is low computing time and low memory consumption. But like all things in life, that rarely happens. So one has to make compromises when you choose an algorithm. So what do we mean by the best algorithm? Well, we have to look at the computational complexity, like we just talked about. We have to look for efficiency in time and memory. But other things can be important too. Is the algorithm really difficult to understand or implement? Can we modify it easily? Will we be able to validate that our code is correct and the algorithm is running correctly? And is it really suitable for the problem that we have? So while computational complexity is extremely important, you have to remember to think about the whole problem. So in summary, algorithm analysis involves looking at the characteristics of the algorithm for different inputs. That's types of input and input size. And you do that so you can predict the performance, compare algorithms, and choose good algorithms. And also understanding how the algorithm works leads to improvements in your algorithm. We usually use computational complexity when we analyze algorithms. And this measures how difficult your algorithm is and how efficient it is. And we look at the time complexity, or the amount of time that the algorithm takes, which is equal to the number of operations, and the space complexity, or the amount of memory the algorithm uses. And there's often a time-space trade-off where you have to compromise on one or the other. Other things you think about when you do algorithm analysis is how difficult the algorithm is to understand, implement, and modify. Will you be able to validate the algorithm easily? And is it suitable to the problem overall? Thank you.